Hey guys, I have been working on trying to get concise videos of the lessons for you all, and I've recorded a few tests, and I'm finding it's going to be best if I just stick to covering the examples in the book and some of the basic concepts. We will then work through the lesson practice and move from there. And you guys are we're going to make it available, make platforms available for you guys to be able to talk with me and ask questions if you have them. Okay, so we're on lesson 94. This week we're going to be doing 94, 95, 96, and 97, and we'll have a test on Friday. Okay, so this lesson 94 is about compound probability. Okay, and I'm on page 640 in your book, and you're welcome to follow along, and that'd probably be helpful if y'all would do that as you're looking at these videos. So we know that the probability of getting heads on one toss of a coin is 1/2, or 1 out of 2. Okay, so 1 out of 2. The probability of getting heads the next time you toss the coin is also 1 out of 2. Okay, these events are called independent events in probability terms. Now, the way that this is described in the book with diagramming is we start with here, our first coin toss, we can get heads or tails. Okay, so this would be toss 1. Now, if we take that same coin, flip it again, we can also get heads or tails, heads or tail on the second toss, and that's toss 2. And I think you guys can see how this would work. Every time you flip a coin, the chance is 1 out of 2 that you get heads and 1 out of 2 that you get tails. Now, the way that we would calculate the probability and the way that we're going to write this is, what is the probability that I get heads on one toss and then say I get tails on the second toss? So if we have this sort of diagram, we call this our sample space. So this will be our sample space for 2 tosses of a coin. So we see here the first toss we get heads, the second toss we get heads, and we've already said the probability of each of these independent events is 1/2, or 1 out of 2. The way that we would figure out what is the probability that I get heads on the first toss and heads on the second toss, we multiply the 2 independent probabilities. 1/2 times 1/2 gives us 1/4. So if we say, what's the probability that I get heads on the first toss and tails on the second toss? So the probability that I get heads followed by tails would also be 1/2 times 1/2, which would give me 1/4. And I think you can see then the probability that I would get tails followed by heads, and the probability that I would get tails followed by another tails would also equal 1/4. Okay. Now, if you look at the bottom, kind of the middle to the bottom of page 641, there's a box that says the probability of independent events occurring in a specified order is the product of the probabilities of each event. And it has right under there some examples. So it says the probability of getting heads, tail, in 3 tosses of a coin would just be multiplying the probabilities of each of these independent events. 1/2 times 1/2 times 1/2, which would be 1/8. Okay? We can line up as many of these as you wanted to, and all you would do is keep multiplying the probabilities of each independent event. And we can do this with a coin toss. The other thing that's in your book is looking at a spinner. Okay. If you have a spinner with 4 congruent quadrants or sectors, okay, like this. If this is your spinner, okay, and you can get 1, 2, 3, or 4 on a spin, the probability of each individual number is 1/4. 1 out of 4 possibilities. So if I said, what's the probability that on a spin I would get a 3 on the first spin, and then I'd spin it again and get a 1 on the second spin? So what's the probability of getting a 3? It's 1/4. What's the probability of getting a 1? It's also 1/4. So the probability of getting these in this sequence would be 1/4 times 1/4, which would be 1/16. Okay. Now, these are also, again, individual events, or independent events. Now, we're going to look at another kind of more complex combination of independent events. And that's looking at the roll of 2 dice. Okay, put this up here. So, the way this works, if I roll, let me straighten this out a little bit. If I roll 1 die, or dot cube, the possibilities are getting either 1, 2, 3, 4, 5, and 6. If I roll another dot cube, I also have the same possible outcomes that it'll land on 1, 2, 3, 4, 5, and 6. If you roll 2 together, then you have combinations that come up. And all the possible combinations are included in this little graph. So I can get a 1 on one cube and a 1 on the other and get 2. I can get a 1 on one cube and a 4 on the other and get 5. I could get a 4 on this cube and a 1 on this one and also get 5. Okay, so there's all sort of different combinations. The likelihood, if I just look at when I'm rolling 1 die, the likelihood of getting a 1 is 1/6. Of getting a 2 is 1/6. A 3, so the likelihood of each of these outcomes is 1/6. The same for these outcomes, 1/6. If I look at the likelihood of getting a 1 and a 1 together, then I'd have to take the likelihood of the first event and multiply it times the likelihood of the second event, and I get 1/36. Okay? Now, if I look at this whole array, this sample space of all the possible combinations that I would get when rolling 2 dice, I see that there's 36 possibilities. But what's interesting with rolling the dice, so if I'm looking at like the example in the book said, what's the chances that you'd roll a 12? Well, there's only one combination of outcomes that would give you a 12. You'd have to roll a 6 on the first die and a 6 on the second one, and you'd get a 12. So out of all the possibilities, 1/6 times 1/6 gives you 1/36. If you all look here, there's 36 squares. So of those 36 squares, only 1/36 would give you 12. But what's unique about rolling dice is there are different ways that I can get different numbers. So I said, what's the likelihood that I would roll a 10? Well, there's 3 possible combinations that would give me a sum of 10. So 1/36 plus 1/36 plus 1/36. So that would give me 3/36 as the possibilities that would result in a 10 for rolling the dice. And then if I reduce 3/36, I can reduce that to 1/12. So then what's the likelihood that I would roll a 10 when I throw 2 dice? 1/12. What's the most common number? Look at that. What would be the most likely number for me to roll when I roll 2 dice? Well, you look, the most common number written here is 7. 1, 2, 3, 4, 5, 6. There's 6 different possibilities that would give me a 7. So if I look at that, so 6/36, we can reduce that to 1/6, which that would be the likelihood of me rolling a 7 when I roll 2 dice. Okay? Now, those, again, are all, this is all the stuff we're talking about here are independent events. And again, to find out the chances of independent events, you multiply the likelihood of each independent event. And then when you have the sample space, like you do in rolling the dot cubes, you can then add up the likelihood of getting a 10 in multiple different ways. Now, the last thing that's discussed in your book is the probability of dependent events, okay? And at the bottom of page 643, the book says when the outcome of one event affects the probability of a subsequent event, the events are dependent. For instance, if a card is drawn from a deck and not replaced, then the probabilities of the draws of any remaining cards are affected by the first draw. So the probability of dependent events occurring in a specified order, it's also the product of all the individual events. But the first event has to then be, the subsequent events have to be recalculated because they're being affected by the first event. So the example they use in the book is of drawing from a card deck. Okay, so a deck of cards has a total of 52 cards. And the example in the book says, what's the chances on 4 draws of a deck? So you take a deck of cards, you draw 4 cards. What's the chance that on 4 draws, I will draw the 4 aces that are in that deck of cards? And that's how many aces there are in any deck of cards. So the first time I draw out of the 52 cards, there's 4 out of 52 is the possibility that I would draw an ace. But what we're wanting to find out, what's the probability that on 4 draws, I will draw an ace, an ace, an ace, and an ace, and then draw all 4 aces in 4 random draws out of a deck of cards. So I'm going to draw the first card. Let's assume it's an ace. So then, what's the probability of my second draw being an ace? Well, there's only 3 aces in the deck, and then how many cards are there left in the deck? There's only 51 now, because I didn't replace this card. Then, assuming these were 2 aces, what's the chance that I would draw an ace on that third draw? Well, 2 aces are gone, so how many aces are left? There's 2 aces left, and how many cards are there now? We're down to 50, okay? And then on the 4th draw, there'd only be 1 ace left in the deck, and if I haven't replaced the cards that I've drawn previously, then there'd be 49 cards left to draw from. So, if I wanted to know the probability of drawing the 4 aces, so the way it's worded, it says from a well-mixed deck of cards, Josephina selected and kept 1 card, then a second card, then a third card, and finally a 4th card. What's the probability that those 4 cards are all the aces in the deck? So this is the calculation that you would have to do. If you do this, the answer comes out to be 1 out of 270,725. I think we can all agree it would be very unlikely if you just randomly drew 4 cards out of a deck that they would be the 4 aces. But this is the actual probability of that event. Okay, so that's a summary of what this lesson's about. I'm going to stop the video now and do a separate video of quickly working you guys through the practice problems just to solidify this concept. And then your homework, like always, is just to do the whole lesson problem set. Okay?